Right now, while you are watching this video, something is moving through a region of space so distant that a radio signal leaving Earth this very second will need almost a full day just to reach it. It is not a new probe. It is not solar powered. It is not guided by artificial intelligence. It was built in the workshops of the 1970s, before smartphones, before the internet, before almost every piece of technology you use today even existed as an idea, and it was never designed to still be running. Yet, in the cold dark beyond the sun's protective bubble, Voyager 1 is still alive. A spacecraft meant for a 4-year planetary tour is now, in 2026, closing in on 49 years of continuous flight. It has punched through the edge of the solar system. It has survived radiation storms, a failing onboard computer, clogged fuel lines, a dying power source, and distances so extreme that a single exchanged sentence with Earth now takes nearly 2 full days. But here is the part that should make you pause. Voyager 1 did not just endure, it kept measuring. And what its last working instruments are still recording from the space between the stars is something scientists did not fully expect to find out there. A faint, unbroken hum of plasma waves, a signature that tells us the void beyond our sun is not empty, not silent, and not nearly as simple as the old models assumed. This is the story of a machine that should have gone quiet decades ago. This is the story of the most distant object humanity has ever built. This is the story of Voyager 1, and in the next few months, it is about to cross a milestone no spacecraft has ever crossed, while still, somehow, talking back to us. Before we go further, let's clear up the title. When people say Voyager 1 turned around, they don't mean the spacecraft physically reversed direction and started flying home. It didn't. Voyager 1 is still racing outward, deeper into interstellar space, at roughly 38,000 miles per hour, and it always will be. What turned around really refers to is the spacecraft's antenna and its instruments turning their attention back toward the unknown region behind the sun's shield, listening to a place no other human-made object has ever sampled from the inside. That distinction matters because it's the difference between a myth and the real story, and the real story is stranger than the myth. To understand why any of this matters, we have to go back to the 5th of September 1977, when Voyager 1 lifted off from Cape Canaveral, Florida, on top of a Titan III IE Centaur rocket. Interestingly, Voyager 1 actually launched 16 days after its twin, Voyager 2, because a faster trajectory let it catch up and arrive at Jupiter first. At the time, the mission plan sounded almost modest. Fly past Jupiter, fly past Saturn, study the planets and their moons, and send the pictures home. Nobody signed up to build humanity's first interstellar messenger. They signed up to build a 4-year planetary scout. Nobody expected this particular machine, with its 1970s-era computers holding less processing power than a modern calculator, to still be transmitting data nearly 5 decades later. It was supposed to do its job at Jupiter and Saturn and then fade into silence somewhere past Uranus. But it didn't fade. It kept going. And every single time engineers assumed its story was winding down, Voyager 1 found a way to keep talking. At Jupiter, in March 1979, Voyager 1 sent back images and readings that rewrote what scientists understood about the solar system's largest planet. It revealed the thin, dusty ring circling Jupiter that nobody had confirmed before, caught active volcanoes erupting on the moon, Io, the first ones ever seen on another world besides Earth, and mapped the chaos of Jupiter's storms and magnetic field in detail no telescope on Earth could match. Then, in November 1980, it swept past Saturn, capturing the intricate, braided structure of its rings, spotting several previously unknown moons hidden in the ring system, and confirming that Saturn's giant moon Titan was wrapped in a thick, hazy nitrogen atmosphere, a discovery that still shapes how scientists search for potentially habitable worlds today. Those two flybys alone would have secured Voyager 1's place in the history of space exploration. But after Saturn, something bigger happened. Voyager 1 didn't stop. Its trajectory after the Saturn flyby bent it up and out of the flat plane where the planets orbit, sending it on a one-way climb toward the edge of everything. It crossed the orbit of Uranus without visiting it, crossed the orbit of Neptune, and kept climbing outward, faster and farther than anything humans had ever launched. Eventually, it reached a boundary most people had never even heard of, the heliopause. That single word may be one of the most important words connected to life on Earth, even though almost nobody outside astronomy knows it. And the sun doesn't just emit light. It also constantly blasts out a stream of charged particles called the solar wind. And that wind inflates a colossal bubble around the entire solar system, a bubble called the heliosphere. Inside that bubble, the sun's influence dominates everything. Outside it, interstellar space begins, filled with the leftover material and radiation drifting between star systems. Every human being who has ever lived, every ocean, every war, every love story, every sunrise has happened entirely inside that bubble. On the 16th of December 2004, Voyager 1 crossed the termination shock, the point, roughly 94 astronomical units from the Sun, where the solar wind abruptly slows down as it collides with interstellar pressure. Then, on the 25th of August 2012, it went further still and crossed the heliopause itself, confirmed by NASA the following year through a sudden, lasting jump in the density of charged particles around the spacecraft. For the first time, a human-made object was sitting directly in the space between stars. That moment changed the kind of science Voyager 1 could do. It was no longer studying interstellar space through a telescope, a model, or an educated guess. It was standing inside it, measuring it directly, particle by particle, and what it found did not match the tidy predictions. For decades, many models pictured interstellar space near the Sun as thin, calm, and largely uniform. Instead, Voyager 1 found density gradients, turbulence, and unexpected structure in a region scientists had assumed would be close to empty and still. Then came the part of the story that gives this video its title. Beginning around 2017, 5 years after crossing the heliopause, Voyager 1's plasma wave subsystem began recording something new, a very faint, narrowband signal that simply would not go away. Researchers at Cornell University, led by then doctoral student Stella Koch-Ocker, spent years combing through this slow trickle of data and, in 2021, published findings describing it as a persistent, low-level hum produced by oscillations in the thin interstellar plasma surrounding the spacecraft. It is not sound the way we hear sound on Earth. There is no air out there to carry it. It is an electromagnetic signature, vibrations moving through charged particles so sparse that a cubic centimeter of that space holds only a fraction of a single electron. Before this discovery, scientists could only measure the density of interstellar plasma when something dramatic happened, specifically when a shock wave triggered by an outburst on the Sun rippled outward, slammed into the interstellar medium, and briefly excited the gas enough to detect. Those events were rare and gave only occasional snapshots, like trying to map a lake by waiting for the rare firework to go off nearby and lighting it up for a second. What Ocker and her colleagues found was different, a continuous, steady emission that let researchers track density changes across roughly 10 astronomical units of interstellar space without needing a solar outburst at all. That is the real discovery hiding behind the dramatic title of this video. Instead of occasional flashes of data, Voyager 1 had, almost by accident, become a running gauge of the density and turbulence of the space between the stars. And what that gauge showed was that the region was not dead and uniform. It had structure. It had fluctuation. It had, in the words of Cornell astronomer James Cordis, something closer to a quiet, gentle rain of activity interrupted every so often by louder bursts rather than pure, unbroken silence. Now, scale that up in your mind. Voyager 1 isn't drifting through a cloud the way clouds drift over Earth. It's crossing the local interstellar medium, the extremely thin material that exists between entire star systems, so sparse it would register as a near perfect vacuum by any laboratory standard on Earth. And yet, across the billions of miles Voyager 1 has already covered, even those tiny variations in density and the invisible hum threading through them reveal something about how our solar system's magnetic bubble interacts with the wider galaxy. That connection is why this story reaches all the way back to Earth. The heliosphere, the very bubble Voyager 1 escaped, is part of what shields the inner solar system from a portion of galactic cosmic radiation, the high energy particles that stream in from exploded stars elsewhere in the galaxy. It's not a perfect shield, and it doesn't block everything, but it is a meaningful buffer. If the interstellar environment just outside that buffer is more turbulent, more textured, and more dynamic than older models assumed, then the boundary protecting our solar system is not the simple, static wall many once pictured. It's an active, shifting frontier where solar wind, galactic pressure, magnetic fields, and plasma waves are constantly negotiating with each other. Voyager 1 is one of only two machines in existence sitting right on the far side of that negotiation, listening in real time. But this mission almost ended for an entirely different reason in November 2023, and this part of the story sounds more like an engineering thriller than a science documentary. Around Thanksgiving that year, Voyager 1 abruptly began sending back telemetry that made no sense, repeating patterns of ones and zeros with no real information encoded in them. The carrier signal was still there, proof the spacecraft was alive and could still receive commands, but every packet of science and engineering data coming home was unreadable static. For months, a small team of engineers at NASA's Jet Propulsion Laboratory worked to diagnose a machine they could not see, could not touch, and could not visit, sitting more than 15 billion miles away. Every single command they sent took over 22 hours just to arrive, and any reply took another 22 hours to come back, meaning a basic diagnostic question and its answer could easily eat up 2 full days. Send a command, wait, hope, analyze. Send the next command, wait again. And every mistake risked being permanent, on hardware nobody on the planet could physically repair. Eventually, the team traced the problem to Voyager 1's flight data subsystem, the onboard computer responsible for packaging science and engineering readings before radioing them home. A single memory chip inside that subsystem, storing a portion of the software, had apparently failed after nearly half a century in the punishing radiation of deep space, corrupting a small but critical piece of code and turning the spacecraft's data stream into gibberish. Think about that. One aging chip, smaller than a coin, sitting inside the most distant machine ever built, had quietly stopped working, and that alone was enough to nearly silence one of humanity's longest-running scientific instruments. The engineers could not replace the chip. There was no way to fly out and swap it. So instead, they did something remarkable. They rewrote the affected code and relocated it, splitting it into pieces small enough to fit into other, still functioning sections of the spacecraft's limited memory, and adjusted the software so all those scattered pieces would still work together as one system. That wasn't ordinary troubleshooting. That was remote surgery on decades-old hardware, performed with commands that needed nearly a full day just to arrive at the patient. And it worked. By the spring of 2024, Voyager 1 was sending back readable engineering data again, and not long after, its science instruments came back online too, once again returning genuine measurements from the interstellar medium. The mission had come back from the edge of silence. But the chip failure wasn't the last crisis, and it won't be the last one either, because the deeper threat facing Voyager 1 now isn't a broken component, it's power itself. Voyager 1 runs on radioisotope thermoelectric generators, which convert the heat produced by the natural decay of plutonium-238 into electricity. That plutonium has been decaying since before launch, and it will keep decaying for as long as the spacecraft exists. Every single year, Voyager 1 has less electrical power available than it had the year before. A slow, steady, unstoppable countdown that started the moment it left Earth. That countdown forces brutal decisions. Engineers at JPL have spent the last decade methodically switching off instruments and heaters, one after another, to keep whatever remains alive for a little longer. Voyager 1 once carried a full suite of 10 scientific instruments. By 2026, only a handful are still switched on, chief among them the magnetometer, which tracks magnetic fields, and the plasma wave subsystem, the very instrument responsible for the interstellar hum this video is built around. Every shutdown isn't just flipping a switch, it's permanently retiring one of the spacecraft's scientific voices, never to speak again. And the power crisis isn't the only mechanical worry keeping the Voyager team up at night. To keep transmitting to Earth, Voyager 1's antenna has to stay pointed at our planet with real precision, and that pointing depends on small thrusters that fire tiny pulses of hydrazine fuel. Some of those thruster lines have become partially clogged with age, reducing how reliably they can fire, and unlike earlier in the mission, there is no longer a healthy backup system waiting in reserve. As Voyager project manager Suzanne Dodd of JPL has put it, essentially everything left on the spacecraft is now single string, meaning there's no redundant twin ready to take over if a critical part fails. If the antenna ever drifts out of alignment with Earth for good, the connection ends immediately, no matter how much power the plutonium still has left to give. Making matters more tense, the one Deep Space Network antenna capable of sending commands to both Voyagers, a giant dish at the Canberra complex in Australia called DSS-43, went offline for a major multi-month upgrade between 2025 and early 2026, with only a handful of brief operational windows squeezed in. That gap forced engineers to race against the clock to revive backup thrusters and stabilize the spacecraft systems before the antenna went dark for maintenance, adding yet another layer of tension to a mission that already runs on razor-thin margins. It's also worth remembering that Voyager 1 isn't alone out there. Its twin, Voyager 2, launched 16 days earlier and took a slower, more looping route past Uranus and Neptune before finally crossing its own heliopause in November 2018, 6 years after its sibling. Both spacecraft are now confirmed to be flying through interstellar space, making the Voyager program the only mission in history to have two independent probes gathering data from outside the Sun's bubble at the same time. But Voyager 1 remains the record holder, the farthest and the fastest of the two, out ahead by billions of miles and still pulling away. Whatever Voyager 1 finds first, Voyager 2 tends to confirm a few years later from a completely different direction, which is part of why scientists trust these interstellar readings as something real and not just a quirk of one aging instrument. And now, after everything Voyager 1 has survived, chip failures, clogged thrusters, antenna outages, and a slowly dying power source, it is approaching a milestone that has never happened before in the history of spaceflight. Sometime around the middle of November 2026, NASA expects Voyager 1 to become the first human-made object to reach a full light day from Earth, a distance of roughly 16.1 billion miles, or about 25.9 billion kilometers. A light day is exactly what it sounds like. The distance light itself covers in 24 hours. Once Voyager 1 crosses that threshold, a command leaving Earth's Deep Space Network dishes will need a full day just to reach the spacecraft, and any response it sends back will need another full day to return, turning a single exchange into a 2-day round trip. As Suzanne Dodd described it, if her team radios "Good morning" to Voyager 1 on a Monday morning, they won't hear anything back until Wednesday morning. No spacecraft in human history has ever remained operational and in contact at that kind of distance before. To put the scale in perspective, when Voyager 1 crosses the one light day mark, it will be about 5.6 times farther from Earth than Neptune. It's currently transmitting data at roughly 160 bits per second, a rate slower than an old dial-up modem, using a transmitter running on only about 23 watts of power, less than a single household light bulb. And that whisper-thin signal still has to be captured by giant radio dishes here on Earth after crossing nearly 16 billion miles of empty space. It is, by any measure, one of the most fragile, ongoing conversations in the history of technology. And yet, Voyager 1 will not stop there. Even once its power finally runs out, likely sometime around the mid-2030s according to current NASA projections, it will not slow down, crash, or burn up. There's no air resistance in the vacuum of interstellar space, no ocean to sink into, no ground to hit. It will simply keep drifting, silent and cold, carrying its cargo through the galaxy essentially forever. NASA estimates it won't reach the outer edge of the theorized Oort cloud for roughly another 300 years, and it will take about 30,000 years more just to pass through that distant shell of icy debris. In about 40,000 years, without ever intending to, it will drift within roughly 1.7 light years of a dim red dwarf star called Gliese 445 in the constellation Camelopardalis, a star currently moving toward our solar system at over 100 kilometers every second. And riding along with it the entire way is the most haunting object humanity has ever launched into space, the Golden Record. That both Voyager spacecraft carry an identical gold-plated phonograph record assembled by a committee chaired by astronomer Carl Sagan, containing images, natural sounds, greetings in dozens of human languages, and music from cultures across the entire planet. It is not a flag, it is not a weapon, it is not a claim of ownership over anything. It is a message, a small golden postcard from a small blue world, carrying the sound of wind, rain, ocean, surf, a human heartbeat, laughter, and songs recorded long before most of the people listening to this video were even born. If, tens of thousands of years from now, something or someone ever finds Voyager 1 drifting through the dark, that record will tell them we existed, that we wondered, that we built a fragile machine out of 1970s technology and sent it out past everything we knew, just to see how far it could go and what it might find along the way. But the Golden Record isn't the only message Voyager 1 is sending. Its scientific data is a message too, one aimed squarely at us right now, while there's still time to receive it. It's telling us the space beyond the sun's bubble has turbulence. It's telling us that plasma density shifts and fluctuates across enormous distances in patterns nobody had directly measured before 2017. It's telling us the edge of our solar system isn't a clean, simple line on a diagram, but a living, breathing frontier where the sun's influence and the wider galaxy are constantly pushing against each other. And maybe the most unsettling part of all this is the timing. We are learning these things at the very end of Voyager 1's working life, not at the beginning, when the mission had plenty of instruments, plenty of power, and plenty of time. We are learning them while engineers are counting watts like they're counting oxygen, while thrusters are clogging, while one whole antenna complex has to go offline for repairs at the worst possible moment, and while a single failed memory chip nearly ended the whole conversation less than 3 years ago. The spacecraft survived just long enough to reach the place where the real discoveries were only beginning. And now, as the mystery keeps opening wider, the machine carrying the only instruments capable of studying it up close is quietly running out of time. That is what makes Voyager 1's story feel less like routine engineering news and more like a race against silence. Every plasma wave reading it sends home now matters. Every magnetic field measurement matters. Every clean packet of data that survives the 15 billion mile trip back to Earth matters, because at some point there will be a final one, a final signal, a final message pulled out of the dark. And nobody will know for certain that it was the last one until the silence afterward simply never breaks. When that day eventually comes, Voyager 1 will not stop existing. It will just stop speaking. It will become exactly what it always carried the potential to be: a silent, golden plated ghost ship drifting endlessly through the Milky Way, carrying the recorded voice of a species that, for 49 remarkable years and counting, managed to keep listening to it across billions of miles of empty space. So, when you hear a title like Voyager 1 turned around and made a discovery we can't explain, here's what the real story actually is. Voyager 1 never reversed course. It didn't stumble onto an alien artifact, and NASA isn't hiding some secret object in deep space. The real discovery is quieter than that, and in some ways more unsettling. The space beyond our solar system is not the dead, empty void classic models predicted. It has a persistent voice, a faint interstellar hum, first identified in 2021, that researchers are still working to fully explain, and the only working instrument capable of continuing to record it is running out of power, running out of thrusters, and running out of time. That is the honest version of the mystery. A machine built nearly 50 years ago, using less computing power than the phone in your pocket, is still carrying our questions into a region no human body will reach for centuries. Still measuring the pressure just outside the sun's protective shield, still proving that our solar system isn't an isolated island but something wired directly into the wider structure of the galaxy around it, and doing all of this while its own light slowly dims. Maybe that's why Voyager 1 feels less like a piece of hardware now and more like a message in its own right. Its power is fragile, its memory is fragile, its thrusters are fragile. Its signal, thinner than a whisper by the time it reaches Earth, is fragile, but what it has already achieved is enormous and, quite possibly, unrepeatable for a very long time. A spacecraft assembled in the 1970s has outlived every prediction made about it, crossed the edge of the heliosphere, survived a computer failure that nearly ended everything, clawed its way back to full science operations, and by the end of 2026 is set to become the first human-made object ever to sit a full light day away from home, all while still whispering back data from the space between the stars. There has never been anything quite like it, and there may not be again for a very long time. So the next time you look up at the night sky, remember that somewhere out past the planets, past the edge of the sun's bubble, past everything humanity has ever physically touched, Voyager 1 is still moving, still cold, still aging, still losing power a little more every single year, and it is still listening. As long as that faint signal keeps crossing the dark and finding its way back to the giant dishes of the deep space network, we still have one living thread connecting us to the space between the stars. One machine, one fading signal, one narrowing window to understand what's really waiting out there beyond our solar system, before the connection finally goes quiet for good. The universe out there was never as silent as we assumed, and Voyager 1 is the reason we now know it. The only real question left is whether we keep listening closely enough before that last signal arrives. If you want more real stories from the far edges of space and science, subscribe, turn on notifications, and stay with us, because the deeper we go into the universe, the stranger and the more human the truth turns out to be.